We've talked about the logistic regression model and the cost function, and you already know how to use gradient descent to minimize the cost function. In this video, we'll talk about a different algorithm called Newton's method, which can sometimes be much faster than gradient descent. This is a cost function for logistic regression, and we would like to minimize j of theta as a function of theta. So one of the ways to find the minimum of a function is to take derivatives and set to 0. In particular, we can take the derivatives of j of theta, and if we can find a value of theta for which the derivative is equal to 0, then hopefully we'll be at a minimum, because that's how you find minima of functions. So our strategy will be to find theta. Our strategy will be to come up with an algorithm that can find theta such that the derivative is equal to 0. And let's see, in order to simplify the derivation in this video, I'm going to run through an example of how we do that with under the assumption that theta is a real number. So instead of using vector value theta, in which theta was an n+1 dimensional vector, I'm going to run through a simpler example where theta is just a real number, and then we'll generalize it to the vector value case later. And concretely, what I'd like to do is define f of theta to be the derivative of j of theta with respect to the parameter theta. And so our goal is to come up with an algorithm so that we can find theta such that f of theta is equal to 0. Okay, because f of theta is defined as the derivative, so we can find the point where it's equal to 0. We've found a place where j of theta has 0 derivative, and hopefully that will correspond to the minimum of j of theta. Oh, and as an aside, if I'm not sure how much calculus you know, but if you're confused about why I'm switching from this notation to this notation, this is the partial derivative notation on the right, and this is the derivative notation on the left. If you don't remember what the difference is, don't worry about it. The difference isn't significant, but it turns out the notation on the left is what you use if theta is a real number, and the notation on the right, that was the partial derivative for when theta was a vector. But again, for the purpose of this video, this little difference in notation isn't important if you don't remember what the difference is. So let's illustrate Newton's method with a diagram. We have some function f, and f is a function of a number theta, and our goal is to find a value of theta such that f of theta equals 0. Okay, and again, the motivation was because we defined f to be the derivative of j, and so we want a place where this derivative is equal to 0. Let me show you what Newton's method does in pictures. Newton's method starts at some value of the parameter, say theta 0, and so imagine we're here. What Newton's method does is it fits a straight line to the function, also fits a tangent to the function, tangent at that point. I didn't draw this very well, but fits a tangent to the function at that point, and then see where it intersects 0. And then this is going to be our next value for theta. It's called theta 1. Okay, so that's one iteration of Newton's method. In the next iteration, we look at where we are now, and then we again, fit the derivative, fit a tangent to the function, and then see where the tangent intersects the horizontal axis, and this is now theta 2. And then we keep going. Look at this, going to fit a tangent, see where it intersects. This then gives us the next value, and we keep going. Here's the fourth iteration for the tangent to the function. There, that gives us theta 5. Then you fit another tangent, and that gives us theta 6, and so on. Let me just write this down. That was what, theta 3, theta 4, and so on. And remember, our goal is to find a point, right, f theta, such that f of theta equals 0. And so our goal is to find this point here already. And you can tell, hopefully, that Newton's method is converging fairly quickly to this point that we're trying to find. This was Newton's method in pictures. Let's go ahead and work out the details of the algorithm for one iteration of Newton's method. In particular, given theta 0, so how do you go from theta 0 to theta 1? So let me redraw a simplified picture here. Right? So let's say this is f of theta, and this is theta 0. So our goal is to find this point where f of theta is equal to 0. And so what one iteration of Newton's method did was, we fit that tangent, see where it intercepted, and this gave us theta 1. So let's figure out what the right math is for doing one iteration of Newton's method. In particular, let me call this horizontal distance, this distance between theta and theta 1, let me just call that delta. So Greek alphabet delta is denoted by a triangle. So theta 1 is going to be equal to theta 0 minus delta. And what I want to do is figure out what is the value of delta. Now, let's notice a couple things, right? First, the height of this point, the height of this is, by definition, this is f of theta, right? Because f of theta is, so it's the height of this function. And in particular, this is f of theta 0. Let's write that properly. So f of theta 0 is the height of that green line. Moreover, we'll look at the derivative of f at this point, right? So by definition of the derivative of a function gives us gradient, and the gradient of this function is defined as this height over this horizontal width. So that by definition, the derivative with respect to theta of f prime of f, and the derivative is often, we'll just abbreviate that f prime. So I'm going to use f prime as the derivative of f with respect to theta. So the derivative at theta 0, this is going to be equal to, this vertical height divided by this horizontal width. And therefore this derivative is equal to f prime, is equal to f of theta 0, which is equal to this height divided by delta, which is this horizontal width. Okay? And so if we take this equation and solve for delta, we get that delta is equal to f of theta 0 divided by f prime of theta 0, because f prime of theta 0 is equal to this fraction over here. Lastly, let's take delta and plug this back in, and therefore this tells us that theta 1 is theta 0 minus f of theta 0 divided by f prime of theta 0. And this is one iteration of Newton's method. Of course, I've written up the update here for going from theta 0 to theta 1. And of course, you do the same thing to go from theta 1 to theta 2 in the next iteration, and so on. Let me just write out the general form, which is one iteration of Newton's method is going to update. So theta t plus 1 is going to be the previous value of theta t minus f of theta 0, f of theta t over f prime, the derivative of f, evaluated at theta t. Now that's one iteration of Newton's method, and just to plug this back into the original problem we care about, we had said that f of theta is the derivative of j of theta, which is why we want to find the value of theta when this is equal to 0. And this thing, let me just write the derivative of j with respect to theta. Let me just write that as j prime of theta. Okay? So plugging this definition of f back into there, what we find is that one iteration of Newton's method is as follows, equals j prime of theta t divided by j double prime of theta t, where j double prime is the standard notation for denoting second derivatives. Great. So this equation gives Newton's method for when theta is a real number, and it turns out to be a very efficient algorithm for minimizing j as a function of theta. Of course, so far I've derived this algorithm just for the case of theta being a real number, and in the next video we'll generalize this to the case of where theta is a vector value, is a vector, and we'll take this idea and apply it to logistic regression.